Welcome to Lecture 18, the Earth and its Mineral Resources. This is the second lecture in Unit 5 of the Introduction to Environmental Science, the Earth's Carrying Capacity. This rather large, imposing structure here, this volcano. It's actually Krakatoa is the name of it. This is an image taken, well, it's not really an image, a lithograph, I guess. It was published in Harper's Weekly in 1883, August 1883. Probably the last image of this mountain as it stood at the time. Shortly after this was recorded or drawn, I'm not sure how exactly they made this, pretty much this part of the mountain went away. It was a very large volcanic eruption, and one of the first volcanic eruptions wasn't the largest. Certainly we've experienced larger in the last century. But it was the first one that recorded a seismic event all around the world at the same time, because we had seismographs stationed all over the place, and this also caused tremendous amounts of ash, soot, rock to be pulverized and put into the atmosphere. It circled the globe for 3 or 4 years, caused interesting sunsets, and suppressed global temperatures, caused some crops to fail, that sort of thing. Anyway, mineral resources, volcanoes. So we're going to talk about the processes that shape our resources. We have a very dynamic planet. We'll talk about those tectonic processes that have brought us to have so many mineral resources on this planet. Mineral resources in society, metals that are essential to our economy, and there are some non-metal mineral resources that are also essential to our economy. We just don't think of them as being minerals. Who consumes most of the world's minerals? Well, you could guess. We'll get there in a minute. Environmental impacts of mineral extraction. How do we get metal from what is mined? There's a process that all metal or the stuff we mine has to go through, and the inevitable environmental contamination. And the question of where's your cell phone come from? Everybody's got one. I hope, I think. Anyway, where's your cell phone come from? So what sort of processes actually shape our planet? We think of the Earth as having this nice solid crust. It's nice and solid there, right there on top. But that's just the very top of it. At the center, at the core, is this intensely hot as the sun, almost as hot as the sun, very dense iron core, solid, but very, very hot. Outside of that is a semi-solid outer core. From the center of the inner core, center of the Earth, all the way to that mantle, that crust, is 6,370 kilometers. That's quite a distance. You don't think of it as being that. It's a long way down to the center of the Earth. This iron core generates the magnetic fields, generates our poles. So if you call this the North Pole and this is the South Pole, they are all related to this magnetic field, this iron core that's in the center of the Earth. So the mantle is just outside the core, less dense and more pliable, but also very hot. So all the way on the outside is that crust that we are so familiar with. So all of that is what makes up the inner parts of our planet. We don't think anything about it because it's always down there. Well, sometimes we think about it. This is what the Earth looked like 200 million years ago. One big continent called Pangea. I like this map. It's really cool because it shows how the current countries kind of were all slammed together. There's the United States, there's Russia, where's Austria? Australia. Australia is way down here, and that's Antarctica. You can see that those are all kind of jammed together. All of this is Africa, so let me outline that right there is Africa. This is pretty much Eurasia. India is this little slamming thing right here. And this is South America and North America. So I've kind of outlined the larger chunks that we now consider continents. what caused this one big continent to separate into the modern continents, the modern countries? Well, movement of these tectonic plates, which I've kind of, in a messy way, outlined on here. So what does it currently look like? More like this. This is a map of the Earth's tectonic plates. You can see this is a North American plate, one big continent floating on top of that plate. South America, Africa. You get Eurasia, which is a really big plate, probably the largest. And you have these smaller plates, the Indo-Australian plate, that's actually one plate, but it moves together. And where these plates meet, you actually have some rather intense areas right along there of seismic activity. There's this thing that goes all the way around the Pacific Ocean called the Ring of Fire. That's where these tectonic plates are doing some interesting things. What are they doing? Well, we didn't really understand what tectonic plates were until, well, gosh, 50, 60 years ago. Drug a thing. Scientists drug something called a magnetometer behind boats. They were trying to find magnetic fields. Submarines, I don't know what they're trying to find. Anyway, remember that iron core in the center of the Earth, very hot. What they found was this zone, oops, wrong thing. Let me get the right, let's use that color. There we go. Let's try that. And it's still not doing what I want it to do. At any rate, you get the idea. You can probably see that there's a zone, actually, where the sea floor was actually spreading out in some places. Not all along the seafloor, but they found these zones that were spreading. What this did was it forced these plates to collide with other plates as they expanded. The magnetometer found these zones of higher magnetism up and down where the seafloor was spreading, because that was where that fresher rock had come from under the Earth. What you have resulting from this are mountains that pop up where these two plates collide, and these subduction zones where one plate will go underneath another plate. This is a graphic of that process. Tectonic plates. So we have subduction zones where one continental plate will dive underneath another continental plate over on this side. And then you have mountains that pop up where these plates, one plate forces the other one up. The Rocky Mountains, the Sierra Nevada Mountains, all along the Andes, up and down the western edge of the Americas, has this line of mountains. All of that is because of this tectonic plate being shoved underneath one and pushing those mountains up. Very much a hotspot for volcanoes. Anywhere along that western side. I talked about the Ring of Fire all around the Pacific Ocean. That's what that is. Hotspot for minerals. All that fresh material coming out of the core of the Earth. Geologists have identified 4,400 mineral species in the Earth. Far more than is found on neighboring planets. I'm not sure how they determine that, because we haven't visited that many neighboring planets. But our Earth is very, very geologically active. We have these tectonic plates that other planets do not have. At least they're not active. Their planet seems to be frozen in place, or at least the continents, if they have them, are. We have tectonic plates that allow that deep magma to come up and form new minerals. Difference between a mineral and a rock. Well, minerals are very specific. They have very specific chemical compositions. Specific internal crystal structure. Curiously enough, ice is considered to be a mineral, but water is not, because there are impurities in some of those things. Metals may come from mineral ores. You can get metal, but metals tend to be conglomerations. Stainless steel is a metal, but it's only been after it's been refined and stuff's been added to it. Once refined, metals no longer have a crystal structure and are no longer considered minerals. Okay. Rocks, on the other hand, are just aggregates of several different minerals, and here are the different forms. Igneous rock is a sort of rock that you get from a volcano. Metamorphic rock are rocks formed under very high pressure, formed by melting and contorting rock. That's where we get those precious metals, diamonds, jade, those things like that. And then sedimentary rock, sandstone is the classic example. Loose grains are consolidated over time by pressure, just to sit underneath a large amount of mass. There's metal that's essential to our economy. Obviously, we all like to have shiny cars. The average car has 2,000 pounds a ton of steel, 240 pounds of aluminum, 50 pounds of carbon. You can read that list. There's some other things, other metals, titanium, platinum, gold. Wow, okay, lots of other metals located in that car. So, gallon of gas costs what? About $2, a little more than $2 a gallon. At present costs fluctuate some. An ounce of platinum. So how much does an ounce of platinum cost? Well, current market values, about $1,000 an ounce. Gold is, well, fluctuates, but it's more than that. So these metals are very expensive. Why are these metals so expensive? I mean, if they're just being dug out of the ground, you'd think it'd be, well, obviously it's a rarity thing. Even in our homes, or our businesses, or our schools, we have gypsum, which is a metal. We have concrete, which is also not a metal, a mineral. Limestone, rock. Aggregate rock. And steel rebar, which is that refined metal. Bricks, we have paint, which contains actually titanium, again, titanium dioxide. We've gotten rid of the lead because lead was very toxic, but that allows the paint, forces the paint to maintain its color. It's how paint does maintain its color. A lot of silica. Most of that is found in the windows of our homes. A lot of copper wiring. All of our wiring, I think, still is copper. We don't use a whole lot of other things. If you're going to be transmitting electricity, ultimately you have to have some way of getting that power to the thing. Although we may have some fancy chargers and stuff like that, the basic wiring in the walls is copper. And then faucets. Why are faucets shiny? I do kind of wonder about that. It has to be shiny. So we have nickel, iron, chromium, molybdenum. Love that word. Basically, the raw materials used in the United States, it starts at 1900 and goes, well, just through 2006. It's a little bit of an old slide. But what you see mostly is that the construction materials, which is most of these metals are construction. Mostly what you see there is we've had a very, very small amount of recycled materials over this time frame, but the amount of construction materials has continued to increase over time. Not a lot of primary metals being used either. You can barely see that line. It's down to the very bottom of that. Bottom line of this slide is a very busy slide. You can probably see that all these numbers are 100%. Basically, that is the percentage of reliance we have on foreign countries for all of those metals. Arsenic is a very important metal. We use a great deal of that, commodity, if you will. Quartz, mica, manganese, all these things, all are imported to the United States from other countries. China, Morocco, Brazil, Canada, Mexico, Swaziland, Gabon. Got a lot of different countries that we import from all over the world to provide it, because we don't mine all this stuff ourselves. Either we don't have these mineral resources, or we aren't willing to do what it takes to get them out of the ground. Going around, at least in our time frame, we talked about non-renewable resources in the last lecture. This is a non-renewable in our time frame resource. Where will we get these minerals in the future? Well, a lot of it's going to be from mining of those untapped resources in many countries. The Andes are very rich in copper. Copper, once again, we have to have that. It's more remaining in the ground, 690 million tons, than has already been extracted, which is 590 million tons, still a lot. The Philippines, very rich in nickel, 18%, very small island nation, 18% of the global supply of nickel is in the Philippines. Once in the Philippines or in that ring of fire, and that's where that fresh material is coming from. Guinea has a tremendous still future supply of iron. But at what cost? Extraction. Guinea is the epicenter, was the epicenter of the Ebola outbreak in 2014-2015. Simandou, Guinea, is the world's largest known untapped deposit of iron. Guinea needs that economic development that mining that iron is going to bring, but it's a third world country. A lot of damage is done. We talked in an earlier lecture about the problems of the Niger Delta. You have the same type of problem, same flavor of problems in Guinea, in this region. We've done our own environmental impacts of mining here in this country. This original, if you've seen the Appalachians, you've probably seen this ridge and this valley, ridge and valley, and it's very pretty up and down there. There are seams of coal, if you look in those dark lines there, buried kind of underneath that mountain. So if we want to look at this whole mining idea, you can come in here and kind of cut a little hole in the side of it and remove that coal by boring into it, kind of that classic idea. Far more efficient is to go from the top down. More efficient. Get at the seams that way. Of course, then you have this spoil coming in here and filling the valley. And then ultimately, you end up with remediation, supposedly. You have that mine waste reclamation, you basically have flattened out that valley. First, physical destruction of the landscape. Coal seams are better removed by taking the top off the mountain, if you're looking for an efficiency. Yeah, you get more that way. A lot of waste. If you look at this looks like the moon. I mean, seriously. Aerial view of the Appalachians. This is a current view. There's nothing that grows on these mine tailings. All of this area is a barren landscape. It's simply not, it's raw rock. Maybe eventually, if we wait long enough, leave it alone, we might be able to get something growing on it. But this is would be from primary succession, and we're a long way from that. This is another moonscape. You might see, look at all this. This is very barren. Another mining area, but this is not in Appalachia. This one is actually in Bartow. Bartow is where we mine a lot of phosphate. And these are the mine tailings, the residuals from a phosphate mine. It is similar if you drive in that part of Florida, central Florida, you'll see these large mountains, these gypsum stacks, and that is where a lot of the waste products from all that mining come from, all that phosphorus extraction. How do you extract it? Okay, why do we do that here in Florida? Well, there's this thing called the Bone Valley, and basically it stretches from Hardy County down into, Hardy County up into Hillsborough County, get my directions right. Lots of fossils, dinosaurs, whatever the animals were, contained a lot of phosphorus, and they're deposited for some reason in this particularly small region, relatively small region of Florida. Basically, this is I-4 here, if you will, and then Hardy County is down here. Wauchula is down in that zone there, and you have a tremendous amount of phosphate deposits in this area. Phosphorus is something that we need. It's a primary part of the fertilizer. Phosphate mining in this area has been going on for more than 100 years. And it has changed, you saw those moonscapes, the landscape of Central Florida, thanks to the work of these machines. So that machine, looks like just a regular old drag line. It's like the size of a track hoe. So you get closer to it and you realize it's really, really big. They are much larger than they appear from the distance, and they move tremendous amounts of material, tremendous amounts of the whatever they have to get to the phosphate. You saw the moonscape. We are doing some restoration. That land will recover, but will it be what it once was? So the moonscapes in Appalachia, are they getting back to where they're being restored to what they once were? They may not be because of the extraction and the change in the structure of the soils and the rock. Here it looks like we have some trees that are growing. It's some moderately successful, but it's nutrient poor area compared to what it was before. So how do we get the ore, the raw rock, if you will, down to the metal? In ore, this is a process called smelting. Some other compound, carbon and sulfur, are found with that metal. And those things have to be roasted out. You have to get rid of those unwanted compounds. Creates an oxide, that metal oxide, and that waste product, which contains the carbon or sulfur or whatever it is. So after these stuff has been roasted, been cooked at a relatively low temperature, then that ore has to be reduced. Basically, you take all of the, burn it at high enough temperature, remove the oxygen, that oxide part, from the metal. And then you have that final product that's going to cool in the absence of oxygen, no oxygen, no air, till it no longer reacts with the air. When you look at the environmental impacts of mineral extraction, you have a lot of waste from those mine tailings. There's water that's going to fall on top of those mine tailings. We'll talk about all the things that are in those mine tailings. They're very highly acidic, very caustic. Not a whole lot of, there may be some bacteria growing in here, but that's not really great stream habitat. Then you go through the process of smelting. Gases, liquids, all kinds of things are produced. So not only is it just the mining process, but the smelting process produces a lot of waste as well. This is a place called the Gold King Mine in Silverton, Colorado. And it first opened more than a century ago, just before we started mining phosphate in Central Florida. And we're looking for gold, silver, lead, copper, those basic things that you mine out of the ground. Operated for about a century, and then it was officially, technically, decommissioned in 1991. Well, it was just closed. They didn't do anything with it except let it sit there. It was not a federal Superfund site, but the mine was being remediated. Superfund meaning that somebody just abandoned the site and walked away from it. Well, the owner was still present. They hired some corporation companies to try to keep what was left in the mine, the waste and the caustic materials and the hazardous stuff, from escaping downstream. So that mine runoff contains toxic amounts of many metals. That orange color is characteristic. Mercury, arsenic, at concentrations that are simply, they're not economically feasible to be extracted, but they're still toxic, very toxic. This runoff had been held on site within the Gold King mine, inside that mine for decades, starting certainly in the early 1990s up until, say present day. But toxic water, as the stuff's caustic, there's a little wood, door or something holding this, the opening this mine closed. Toxic water was leaking from the tunnel leading to the mine. And there was a lot of water, that's kind of a key part here, a lot of water was backed up in the mine. They hadn't sealed the mine from having water in it. So, a lot of water backed up in the mine, got this caustic stuff, toxic water trying to leak out. What happened? Well, contractors have been working to monitor the site. Just kind of a look at that scarp there a little bit more carefully in a bit. In 2015, August, the US EPA decided it was time to do something. They wanted to attempt pumping that water out of the mine and sealing the mine for good so they can take care of it. They wouldn't have to worry about monitoring it anymore. So they're just going to take and pump all the water out of the mine. Well, the mine was breached when they started the work. There's finger pointing as to who did what, but this is the result. All that orange water that was stored in the mine, held in the mine, flowed downstream into the Animas River, which I believe is the water supply for Taos, New Mexico. The volume of water was grossly, vastly underestimated. Turns out that debris pile that had closed off the mouth of the mine was holding back 3 million gallons of toxic wastewater. All that water made it into this river, water supply for Taos. It took a little while for it to clear out. They have since, I believe, finally closed the mine. But all this toxic water flowed downstream to the ocean. I think it goes to the Gulf of Mexico ultimately. So, has this ever happened near here? Well, actually, recently, more recently than the Gold King mine, this was observed. I think we had a picture of this previously. That is a sinkhole in the top of a gypsum stack, if you will. The Mosaic Phosphate Mine in Polk County. It's a sinkhole that drained at least 3 million gallons at the other mine, at the Gold King mine. 215 million gallons of phosphate wastewater was drained to the upper Florida aquifer. Got a pop quiz, all right. Talking about metals. Online research and math are required for this. So, got the drop box is going to be open when you've finished reading this lecture, seeing this lecture, listening to it. All right, talking about cell phones. If each cell phone contains just 0.03 grams of gold, it's fairly small, how much gold, grams or kilograms or tons, however you want to put it, is there in the 5 billion cell phones on the earth? Maybe more than that. How much gold is in there? That's one question. A little math involved. And the second part of this is where the research comes in. What are the 15 elements or earth metals found in cell phones? Once again, drop box is open. So we have about 5 billion cell phones on the earth, 1 billion computers. I thought there'd be more than that too. But cell phones contain all of these things. You read that list, everything from gold to lithium and mercury. And they also contain some stuff called coltan, which is mined in Guinea. That same place where that Ebola outbreak was. It's an ore containing columbum, yeah, I'm good at that, talantum and niobium. Very important for something we need in cell phones. So I already answered that question. Coltan is mined in Guinea. It includes rare earth metals, niobium, dysprosium, lanthanum, and yttrium. Critical to our cell phones, though. So where does our cell phone come from? Parts of it come from Guinea. When you look at the impacts, once you've mined, you have why do you have so much waste? Well, a metric ton, about 2,000 pounds, about the same thing, of any ore, in terms of you're looking at mining gold, a metric ton may yield only 0.3 of a gram of gold. So you have this tremendous amount of spoil, tremendous amount of water extraction. And then all these materials have to be smelted. That process of smelting where you roast first and drive off the carbon and the sulfur, and then you reduce heat under very high pressure. All this has to happen and produces even more waste. So where do all of these electronic chips and things, essentially gold, we saw it gold, platinum, silver, all that sort of stuff, is found in little bitty quantities in each of these chips. Does this all just end up in the landfill? Well, it could be toxic if it's exposed to water. It's considered e-waste. There are opportunities to dispose of this. Locally, there's an opportunity twice a year in this county. We have a household hazardous waste disposal day, and citizens, residents, are encouraged to, if they have an old, rather than throwing something by the side of the road or drop it in the garbage can, because that doesn't get sorted out, you have the opportunity to actually recycle it and have this material removed and reused, because it's probably cheaper to get it out of these recycled circuit boards than it is to actually go back and dig it out of the ground. Talked about processes that shape our resources. Earth is one of the most dynamic planets that we know of. Well, it's our home, of course, we love it. But it's very dynamic because of the process of plate tectonics, where you have one plate subducting under another plate, and then that plate shoving up mountains. Lots of minerals come from this source. This is where the Earth's minerals often come from. Talked about the metals that are essential to our economy and where we get them from. We get them from other countries for the most part. And who consumes the most of the world's minerals? Well, we do. We get them from other places. We looked at the environmental impacts of mineral extraction. And how do we get metal from what is mined? That's the process of smelting. We talked about a few examples of environmental contamination, from Gold King mine to phosphate mines and other places. And that pop quiz, where does your cell phone come from? Or more specifically, how much gold is there in the world's 5 billion cell phones? You can answer that question and put in those 15 elements. That's 10 points added to, if you get all 10 points right, to the grade for the unit test. It's extra credit. It's worth almost a letter grade. So finish that up, fill it out. These are the references for this particular lecture. Crying foul in Guinea. Pretty good.